guys, I had a request to go over the first 4 problems in this 6.8 worksheet. I also want to take this chance to talk about the different equations, so where confusion basically might come from. So this is the equation, the top one that we used in 6.7, and you'll notice it's the sum, or the change in enthalpy is equal to the sum of bond enthalpies of bonds that are broken minus the sum of bond enthalpies of bonds that are formed, which the way this ends up, the bonds that are broken are reactants, the bonds that are formed are products. The reason we're subtracting the products from the reactants is that when bonds are broken, we have to put in energy, so it's endothermic and it's positive, so the bond enthalpies are positive, whereas when we form bonds, it's an exothermic reaction. It releases energy, so that sign is negative for the bond enthalpies. So that's why we subtract the bond energy or enthalpy of products from the bond energy of reactants, okay? In 6.8, we kind of flip that around. So we are subtracting the sum of the heat of formation, standard heat of formation for products minus the sum of the standard heat of formation of reactants. And the reason that we do reactants subtracted from products is that the heat of formation for reactants is going to be the opposite sign because we're not forming reactants, we are breaking them up. Whereas the heat of formation for products, since we are forming those products, it would be the same sign as those heat of formations. So that might be where some confusion is. It's not always going to be whatever the value is of reactants minus products. In the case of 6.8 with heat of formation, it's products minus reactants. So you just kind of have to think like logically, what is heat of formation, what is bond energy? Heat of formation is the energy it takes to form those things. So if you're forming them, it's going to be the same sign. If you're breaking them apart, it's a different sign. Whereas the bond energy, that's the energy that goes into making or breaking the bond. So if you're making the bond, you have to put in, if you are making bond, it releases energy because it's exothermic, so that sign is negative. Whereas if you are breaking bonds, you have to put in energy, it's endothermic, so it's positive. So hopefully that helps to clear things up a little bit. But now to the actual problems. Number 1 states that using the enthalpy of formation values of the appendix in your textbook, which is on page, I think, 1059 is what I said, in the appendix in the back, calculate the enthalpy of combustion of 1 mole of ethane at 25 degrees Celsius, which is standard. So, I'll erase these. Based on the values in the back of that equation, I'm going to be subtracting the sum of the heat of formation of products minus reactants. And these do depend on coefficients. So my heat of formation is going to be equal to, I am first looking at CO2, which is a product. The coefficient from CO2 gas is 2. If I look in the appendix of the textbook, the standard heat of formation for CO2 gas is negative 393.5 kilojoules. That's really per mole. I have another product, which is water, and I have 3 moles of water. So to that, I'm going to add 3 times the heat of formation of water. And I look to double check because it is water liquid, not water gas. So when I look in the back of the textbook, I have to make sure I'm looking at the formation of water liquid. In the back of the textbook, that value is negative 285.83. Again, that's kilojoules per mole. Okay, so that is the first part of the equation, the sum of the enthalpy of formation for my products. Then from that, I'm going to subtract the sum of the enthalpy formation of reactants. So looking at that chemical equation that they give us, I have 3.5 moles of O2. O2 gas, which if you remember, O2 gas is the most common form of oxygen at standard temperature and pressure. So that sum information is going to be 0. If you also look in the back of your book, it's going to be listed as 0. If you ever just like forget that off the top of your head, that is 0. Plus, I need to do 1, that's the coefficient in front of ethane, C2H6, and that's ethane gas. So I'm going to look in the back of my book for ethane gas, and that heat of formation is negative 84.63 kilojoules. Okay, so the heat of formation of my products minus the heat of formation of my reactants. If I plug these into my calculator, usually I do the products all together and the reactants all together and then subtract them from one another, just because this is a lot of parentheses going on. When I add those together, I find a delta H of a reaction to be negative 1,559.9 kilojoules per mole. And that's per mole of reaction that happens. So for every mole of reaction that follows the reaction that was listed on number 1. If you round, you can easily round to 1,560 as well. Not too worried about sig figs or anything like that. Okay, so that is number 1. Number 2 is going to be very similar. This time we are doing the formation of carbon dioxide from graphite and oxygen gas. So first I'm going to take my heat of formation value of CO2 gas. The coefficient for CO2 is 1, so I'm going to take 1 times again. If you look in the back of the textbook, the heat of formation for CO2 gas is negative 393.5 kilojoules per mole. Okay, so that is all that I have for my products. From that, I'm going to subtract the sum of the heat of formations of my reactants. If you look at the two reactants we have carbon with graphite and O2 gas. Both of those are the most common form of those elements at standard temperature and pressure. So both of those heat of formations are going to be 0. But again, if you forget that carbon graphite is the most common at standard temperature and pressure, if you look in the back of your textbook, it should be given as 0 anyway. So there's 1 mole of those. So I have minus 1 times 0 plus 1 times 0. So basically plus or minus 0. So if I take negative 393.5 kilojoules per mole and subtract 0, the heat of formation for this reaction is negative 393.5 kilojoules per mole. Okay, and this is just showing you that the heat of formation of carbon dioxide from the most common elements is the same as that heat of formation value that we see in the back of the textbook. So that's, I think, the point that they're trying to make with number 2. Number 3, we are doing the same process. This time it is the heat of formation to convert water liquid to water vapor, so liquid to gas. So we're basically going to find the energy that that takes. Now before I find my answer, I'm going to kind of be thinking, okay, liquid water to liquid gas, is that going to take energy or is it going to release energy? So I think when I want to make tea, when I'm boiling water, I have to add energy to that liquid water to make it boil. So I expect this answer to be endothermic, so me having to put in energy. So I do expect my answer to be positive before I even start. So if I go to the back of my textbook, I look at the enthalpy formation of my product, which is gaseous water, and that is equal to 1 times negative 241.82 kilojoules per mole. Okay, and that is all the product that I have. From that, I'm going to subtract the standard heat of formation for my reactants. If I look in the back of my textbook, that is negative, well, it's really 1 times negative 285.83 kilojoules per mole. Okay, I plug that into my calculator, so negative 241.82 minus negative 285.83, and I get a delta H equal to 44.01 kilojoules per mole. Okay, first thing I notice is that this is a positive value, which makes sense because what I said before when I was thinking about when I have to boil water, you have to input energy. So you expect it to be positive because it is an endothermic process. So since we got positive 44.01, positive number, I feel pretty good about that. Number 4, we are doing the exact opposite. They want to know the standard enthalpy change for the formation of liquid water from water vapor. So now we're going from gas water to liquid water. This is going to be basically the opposite process of this, okay? So I'm basically condensing water from gas to liquid. This time, remember, it is products, the standard heat of formation for products minus the standard heat of formation of reactants. My product in this case is liquid water, which has the standard enthalpy value that I listed here for problem number 3. So these two values are basically going to change. I am subtracting 1 times negative 285.83 kilojoules per mole. And from that, I will be subtracting, I forget that value, negative 241.82. Okay, so when I do that, negative 285.83 minus negative 241.82, I get an answer, a standard enthalpy change of negative 44.01 kilojoules per mole. So it's kind of like what we're doing with Hess's law in 6.9, where they're saying if you flip that equation, you have to flip the value of that delta H. That's exactly what's happening here. We're doing the opposite chemical equation, so we notice our sign of delta H changes. Okay. Hope that helps for numbers 1 through 4. Let me know if you have any other questions or if you need a repeat on any of the answers for the worksheet 6.8.